In this tutorial, I'm going to cover contour lines, and this is one way to represent terrain. Recall that contour lines are lines connecting all points of equal elevation above or below a known or assumed reference point or plane. So in other words, you have some sort of coordinate system, and these points have numerical values which are based off of this coordinate system. And there is a line that is drawn that connects all the points of equal elevation, which forms a contour line. So I'm going to give you some examples of how contour lines are delineated, and when you go out to draw contour lines, how you should probably draw them. So existing conditions is one type of contour line that you may have to draw. Existing conditions contour lines are drawn as dashed lines and are usually gray. So this is an example. We have several contour lines here. They're dashed and they are of a gray color. Proposed contour lines are drawn as solids and are usually black in color. So in this example, it's the opposite of black, which is white. So we can see here they're a solid color compared to our existing conditions, and they're supposed to be black, but here they're white since it's the opposite color. And we can kind of see visually why we want to do something like that is because existing conditions is kind of pulled to the back, and this proposed design that we're trying to implement is pulled more forward, so we can see these proposed lines kind of stand out a little bit. Contour labels, historically when drawn by hand, were placed on the high side of the contours. So we can see here this is contour with elevation of 100, this is 101, and the label is written on the high side, not the low side of the contour. So in this case, as we get towards the bottom part of this slide, it's higher in elevation, and when we get to the top part of the slide, it's lower in elevation. So the contour labels are on the high side of that contour. And today in Civil 3D, sometimes the contours are inside the contour line, which is okay. But historically, when we had to draw this by hand, this is how we did it. Then there's something called contour intervals. And contour intervals may vary depending upon the number of contours on the map. So if you have a lot of contours and they're packed in there really tightly, you might want to do like maybe every 10 foot instead of every 1 foot. So for this example, we can see that it's every 1 foot contour. And we usually use a nice even number like 1, 2, 5, 10, or 20. We don't use something kind of difficult to interpolate. And sometimes it may be necessary to do that. And the other thing that we do is we kind of make every fifth contour line a little bit thicker. So we can see here this one was 100, so it's a little thicker. Over here was 105, and it's a little bit thicker. And both the existing and proposed contour line is made a little bit thicker for readability. And then sometimes some places like to add what I call ticks. And this helps us to see when the proposed grade is starting and ending, where this proposed contour line is starting and ending. So the next thing I'm going to talk about is how to read contours, and this takes a little bit of practice. It can seem easy at first, but you can be easily tricked with more sophisticated terrain types and end up making a costly mistake. So you want to be very, very careful. So the best way to overcome challenges when reading contours is to take sections. So I've created some examples here. Our first example is fairly simple. We look at the bottom half of this image, and these dashed lines are the existing contours. We have 10, 9, 8, 7, 6, 5, 4. And then these solid lines here is what we're trying to propose. So now if we go up here and we look at our section, we see this dashed line that's running down like this, and that's our existing conditions. And we can see that it's going to be a uniform slope. There's nothing going on with our existing condition contours. But for whatever reason, we had to add this stepping effect here with this bold line. And this is, if we move the contours in this way, this is what it would create. And we see up here the word called cut, and we have another word over here called fill. And what this simply means is if you move the contour towards higher elevation, like proposed contour 8 is doing, you're going to create what's called a cut situation, and that means that you're carving into the earth. Now if you move your contours in an area that is lower in elevation, like we see over here with proposed contour 7, 6, and 5, then you're creating what is called a fill type situation. So we have to bring in earth and fill it in. And what we end up doing is we end up taking the stuff from cut and we use that as fill. So here's example 2. We have contours that are really close together over here, and then they gradually become spaced apart. And we can look at our slope, like over here. Our slope is really, really steep between contour 7 and 8, but then when we look at the slope, the distance between contour 3 and 2, it's pretty flat. And this is what it looks like in plan view. We have 8, 7, 6, 5, 4, 3, 2. So over here is much higher in elevation, and over here is lower, and it kind of creates this concave shape. And then this one is the exact opposite. Now we're starting lower elevation and we're going to higher. As we get higher in elevation, the contours become more spaced apart, kind of creating this convex shape. Here's another example. So this is kind of like a hill. Well, it goes up towards the top. We're at contour 9, and then it goes back down. And here's another example of the exact opposite of the condition we saw before. We can see that it goes 10, 9, 8, 7, and then 7 starts again, 8, 9, 10, and we can see it kind of creates a ditch-like situation. One thing that I want to mention is that water runs perpendicular to contours. So in this ditch-like situation, we can see that water would run along this kind of like ditch-type area. If we had water that was coming down the side, it would run perpendicular to these contours. Here's an example of a hill, and this could also be, this is kind of like a mound. This also could be like a pond. And we know that this is a hill because we can see from the contours, they get bigger as they get towards the middle circle. If the contour numbers were getting smaller as we get to the middle circle, then we know that this is a pond type situation. And we can see from our section here that this is clearly a hill mound type situation. Here's another example. So it's kind of like a cliff. We have 9 up here, and then it gradually goes down to 8, 7, 6, 5, and we can see from our section what that's doing. So to summarize this presentation, all points on a contour line have the same elevation. Contours closing in on itself within the limits of a map is either a summit or a depression. And contour lines generally do not cross each other. The only time that this may happen is if you have a cave-like space going on. So generally what we're trying to model is the bare earth, so we won't have any cave-like spaces. Contours close together indicate a steep slope. Contours spaced far apart indicate a flat area with a slight grade. The steepest area will be perpendicular to contours. So if you go back here and we look at this, if we have a situation where if we drew a line from here to here, and then we drew another line from here to here, we know that that second line that we drew is going to be much more steeper than that first line, because we can tell from the contour spacing. So the spacing from here to here is much more greater than the spacing from here to here. The same is especially true from here to here compared to here to here. And then water flows perpendicular to contours.